Hey everyone, and welcome back to another AP Calculus video. Today we're going to continue our lessons on finding volumes of three-dimensional shapes. So let's kind of review what we've talked about so far. In the first volume video, we talked about finding the area of something that has a flat base that is carved out by some sort of an equation, and it has some sort of cross sections, it's almost like you're looking down upon it if you're a drone in the sky looking down. And these cross sections that are kind of coming up at us out from the paper could be squares, they could be semicircles, they could be any shape really, but the really common ones that we have are squares, semicircles, isosceles, right triangles, and rectangles. And so these are all what we consider flat-based solids. Another kind of solid that we've talked about is what we get when we take a curve and we rotate it around an axis. And we're still using this concept of having some sort of area function, but this time when we revolve a function around an axis, it's almost like a lathe, right? So we picture, that table leg spinning on a lathe, and if we do a cross section, it's a circle. So we're still integrating the area of the cross section from point A to point B, but now our area formula is just a circle. So based on whatever the shape of the cross section is, when we slice it down, what shape do we see? That's the area formula that we're integrating from point A to point B. And depending on what we're perpendicular to with our cross section, that's going to determine our setup. So we talked about if we have cross sections that are perpendicular to the x-axis, this is certainly the most common scenario, we would set it up with a dx setup, we would say. And that means that everything, including our limits of integration and the area function itself, would contain functions of x, things in terms of x. Everything is x. Now, if our cross sections are perpendicular to the y-axis, we would use what we call a dy setup, in which case we would want functions in terms of y. So all of our equations would contain the variable y. We'd have to solve and get x equals some function of y. We would also use the limits of integration from a lower y value to a higher y value. So depending on the setup and what we're perpendicular to, that's going to determine how we need to manipulate our functions to be able to use them. Today, we're going to talk about a special case of discs where we refer to them as washers. And so this is a kind of a scenario, and you'll see what I mean when I say a washer. Because you see, a disc we think of as being just a solid thing. It's like a plate. A plate is a disc, or a frisbee is a disc. So it's just a solid circle. But what a washer is, it's one of those things that kind of goes under when you're putting like a screw or a bolt in. A washer goes in and it does two things. It protects the material that you're trying to drive the bolt into, and it also distributes the force of the head of the bolt. That's neither here nor there. But basically what a washer is it's kind of like a donut-shaped kind of thing. So let's take a look at a scenario that would create a washer. And really, again, just to make sure that you guys know what a washer is, if that's a disc, a washer just is a washer with a hole cut out. That's all it is. And so we're going to have to consider now, we're going to have a longer radius that goes to the outer edge. We're going to refer to this as big R. And then our hole, basically we're going to have to cut out the hole. So if you think about what's happening, in the same way that when we did the area under the curve and we said, hey, we're going to take the greater area and subtract away the area below it, and that gives us the area between. In the same way, we're going to take the area of the big circle and basically cut out the area of the inner circle. So we're going to have two area formulas, one for the big one, and then we're going to subtract away the little circle. And that's going to leave us with this kind of washer-shaped. So this gray area would be what's left, right? So we're cutting out the hole. So let's take a look at what's going to go on with this equation. So we've got a solid created by revolving the area enclosed by the curves y equals the square root of x plus 1, x equals 4, and y equals 1 about the x-axis. So let's erase this. Let's get a little space on our canvas here. Essentially what we're going to be doing is we're going to take this area that's enclosed by the curves that I've graphed. So this is the area, and we have our nice little intersection points. I'll leave those so we can read them. But basically we've got this function here. This is x equals 4. So that's my blue line. The green line is y equals 1. And we're going to be revolving this about the x-axis. So I always like to mark my axis of revolution with one of these little symbols. And sometimes I'll even come through and I'll put a little dash line just to show that it's not a boundary, it's an imaginary axis of revolution. And as we rotate this shape, this gray shape around, we get this kind of mirror image on the other side. I always like to sketch that mirror image. And it kind of looks like this. There's my mirror image. So you can see that we have this empty space in the middle. And that's the smaller circle of my washer cross section. So what I do is I envision if I were to draw a cross section, remember my cross section is always perpendicular to the axis of rotation. So this is my axis of rotation. I'm going to call it my AOR for short because I don't want to write all those words every time. My axis of rotation. So I'm going to draw my little cross section. I'm just going to draw a line, and this is like looking at the side of the disc. If we flip the disc around like that, we would see that it's a disc with a hole in it. We call it a washer. That's really all. It's a donut, a washer. I don't know, donuts sound more delicious, don't they? So let's determine a few things. So I have to figure out, there's a big R, that's the R that extends to the edge of the curve. And anytime we extend from an X or a Y axis to the edge of a curve, that's always going to be the distance of a function. So let's make sure we make note of that. Anytime we make a radius, or anytime the distance, we consider the distance from an X or Y axis is always a function of some sort. So here, this distance is the distance from the x-axis to the pink function. Well, the pink function is this, or the red function is this square root of x plus 1. So I'm going to make a couple of notes here. In my washer, the big radius, the longer radius, remember the radius always goes from the axis of rotation to the edge of the function. So that's another note we can make here, is that when we're trying to find R or big R will always be the distance from the axis of rotation, which is not always the X or Y axis, by the way. We're going to see that. It's always the distance from the axis of revolution to the edge of the curve. So here we've got two edges. We've got the longer edge. We're going to call that big R. Little r is the distance from the axis of rotation to the inner edge. So that's this distance here. This is little r. So if I zoom in, big R goes to the outside, little r goes to the inside. Little r is the distance of the empty space, right? So let's think about this. Big R is going to be that function, square root of x plus 1. Little r is just 1, because it's going to that line, y equals 1. It's a function. It's the green function. It's y equals 1. Now, one thing we failed to do here in the beginning is we failed to walk through our steps, and that's on me. We need to decide, first of all, is this a dx or a dy setup? And then we need to figure out a of x, which is what I jumped right into. I got a little too excited and carried away. So let's make sure we understand that this is, in fact, a dx setup, because I'm perpendicular to the x-axis. So I'm perpendicular to the x-axis. That's how I know that this is a dx setup, okay? So everything's going to be in terms of x. All of my equations, r is going to contain only the variable x, and I'm going to use limits of integration involving x values. So my next step is to set up my integral. So I'm going to integrate, and I'm going to integrate from the left x to the right x. So here it looks like I'm going to integrate from 0, that's on the left-hand side, up until 4. So that's my right-hand boundary. So 0 to 4. And then my a of x is going to be big pi r, or pi big R squared minus pi little r squared. So that's the area function that I'm going to integrate. So I'm going to go ahead and wrap this up in some nice brackets here. So I'm going to do pi, and then in some parentheses. I like brackets on the outside so that when I do parentheses, they're rounded. It delineates what's going on here. So big R is square root of x plus 1 squared. And then I'm going to take away, I'm going to cut out the inner circle. So pi, and then little r squared. That's my setup. And I'm going to plug that into my graphing calculator to be able to get my final answer here. So let's see what it looks like. So when we plug it into our calculator, we want to make sure we use lots of parentheses. Remember to square the big R and the little r. Don't leave out that exponent. And notice that on my calculator screen, everything is wrapped up. I included pi both times. Now, some teachers and some methods will tell you to put the pi on the outside. You certainly can factor out the pi and put it on the outside. The danger in that is when we go to evaluate, oftentimes we will leave the pi out and we'll get the answer wrong because we fail to multiply by pi. So please, please, please do not forget about the pi. If you choose to pull it out and factor it out of the integral and even put it on the outside of the integral, that's totally fine. It's just dangerous in terms of plugging it into your calculator and just kind of losing track of it and then getting the answer wrong, even though you knew it was supposed to be there. So now what we're going to do is we're going to take a look at the same problem, but this time instead of revolving around the x-axis, we're going to see what it looks like to take this and revolve around the y-axis. Now, when I revolve around the y-axis, I get a slightly different answer. And the slightly different answer comes in the form of the integral setup. And actually thinking about this, it makes me curious. If it's the same shape and I'm still revolving it and it's the same quantity in terms of our cross-section, I wonder if the volume will actually turn out to be the same value, even though we set it up with a different integral and we're revolving it around the y-axis. So let's find out. So revolving this around the y-axis, here is the shape. This is the solid. And as I revolve it around, I'm going to get this cross section here, or sorry, this shape going on. There's my reflection, right? And as I revolve around the y, what this is going to do is this is going to change my problem into a dy setup, because now my discs, my washers, are going to be perpendicular to that y-axis. So now I'm going to have a wider washer, and it's going to just create a different, a different setup. So let's see, we're going to figure out what is our R, what is big R, and what is little r. So remember, big R always goes from the axis of revolution. Well, that's this axis of revolution. It's always going to go from the axis of revolution to the outer curve. Well, here my outer curve is that blue line, and we said that the blue line was x equals 4. So here, big R is going to be 4. All day long, it's 4. That curve doesn't change. Now my inner function goes from the axis of revolution, or my little r, goes from the axis of revolution out to this red curve. Now the tricky part here is that since it's a dy setup, I have this equation, y equals the square root of x plus 1. I'm going to need to solve it for x equals to be able to use it in my integral. So I'm going to have to subtract 1. I get y minus 1 equals the square root of x. When I solve for x, I'm going to square both sides. I get y minus 1 squared. So there's my equation that I have to use. So that's the function. Anytime we go from an x or a y axis to a curve, it's the function. So here, little r goes from the axis of revolution to the inner curve. And it just so happens to be the function. So here, little r is going to be that y minus 1 squared. So my a of x equation that I always need to find is going to be that pi big R squared minus pi little r squared. So I'm going to take big R and little r and put it into my integral. And we're going to evaluate. And generally, we're always going to use our calculator for these. Sometimes they're okay. The other thing we need to consider is we are now also integrating with respect to y. So we need to integrate using y values. So here my y values are going to go from 1, because this green line is at y equals 1. And we're going to go up to that top point, that top value of 3. So my integral values change. So I'm integrating from 1 to 3, and I'm going to do pi times big R squared minus pi times little r squared. Ooh, and this is tricky because I have nested parentheses. It's okay. Sometimes that happens. So here, let's make sure we can see all of the work and it's not behind my face. This is the integral that we're going to go ahead and plug into our calculator, and here's what we get. And you can see that even though we are revolving around the same face, because of how we're revolving it and because of how those radiuses change and the width and everything, the volume does change even though it's the same shape. So we want to make sure that we understand that the axis of revolution, the radius, and where we're revolving plays a big deal in the volume and the size of the shape that we're creating. Even though it looks like we're taking the same amount and revolving it, we're revolving it differently, and it creates a different shape with a different volume. You'll also notice that in the calculator, I plugged in the variable x instead of the letter y. Remember, our calculator only speaks the variable x. So even though our setup, when we write it out on our test, we need to make sure we include the variable y, when we go to evaluate in our calculator, we'll enter every y value as just the letter x. It's just changing the letter and evaluating it, but it should be just fine. So now let's take a look at what happens when we revolve a shape around something other than an x or a y axis. So here we're going to find the volume of this solid that's created by revolving this region bounded by y equals x squared, that's the red curve, and y squared equals 6x, that's the green curve. So we have two parabolas, one that's vertically oriented and one that's horizontally oriented. We're going to take this quantity right here, shaded in gray, and we're going to revolve it around the line x equals 3. So the first thing I'm going to do is I'm going to make a dashed line to represent my axis of revolution, x equals 3. And I'm going to make sure that I label my axes very clearly here, because I don't want to get confused, especially when I don't have lots of fun colors to work with and I'm only working with a pencil or a pen, preferably a pencil, and everything's the same color. I want to clearly label that axis of revolution, and I'm even going to go so far as to put that little symbol around it to show, hey, this is where I'm revolving. And then I'm going to make sure that I sketch a little cross section. So over here, or sorry, cross section, I am using the wrong word. I'm going to sketch a little mirror image, right? So it's going to kind of look like this. Doesn't have to be perfect, but the idea is I'm revolving it that way. And I need to do all of the normal steps that I would normally do. So step 1, I'm going to decide if it's dy or dx. Step 2, I'm going to determine what is my a of x function, including r and big R and little r, because this one, there's a hole in the middle, clearly. This is a washer type setup where I'm going to have a big circle and a little circle, and I need to subtract that little inner empty circle out. And then finally, I'm going to set up my integral. So let's walk through and determine if it's dx or dy. My cross section will always need to be perpendicular to the axis of revolution. So since my cross section is perpendicular to the axis of revolution, it is also perpendicular to the y-axis, making this a dy setup. So I'm going to need to make sure that all of my equations are solved for x. X equals some function of y. I'm going to need all functions of y, and I'm going to need my limits of integration to be my y values. So that decision has been made. Now we're going to determine big R and little r. And we're going to remember a few things. We're going to remember that the distance from the x or the y axis to the curve is always the function. Big R and little r is always the distance from the axis of revolution to the curve. So let's draw a couple things in here. First of all, let's draw big R. Big R is going to be this entire golden distance here. This is big R. It goes to the outer curve. Let's sketch little r in. Little r is going to be this distance right here. This is little r. It goes to the inner curve. Okay, so we need to know, and maybe drawing it on this side, let me back up a little bit. We're going to draw it on the other side to where we can actually draw it to the curves that we know. Just remember, big R is symmetric, so big R is this, and little r is this distance. Now, notice that we're not extending from the x or the y-axis. So big R and little r are not the functions. If it's the function, it's coming from an x or a y-axis. Here in this case, since it's dy, we're going to be concerned with coming from the y-axis. So I'm going to label where the function is, and I'm going to zoom in to do this. And I'm going to label this little green distance here. This is the function. That's the equation, and it's the green equation, and it happens to be this guy right here. That's this distance. Now I need to take it and solve it for x, so I'm going to rewrite it as x equals y squared over 6. That's that distance, y'all. That's that function. It's the green function. Now I'm also going to label in here the other function. So this red function, this distance to the red curve is this. Now I need to solve it for x equals because it's a dy setup, so let me go ahead and do that. X equals the square root of y. That's that pink distance there. It's the square root of y. So what I need to do is I need to look at this and write in a couple other things. And here's the key piece of information that I'm going to remember that's going to help me. All these little line segments, whatever I use them for, they are going to help me do some geometry, right? So I'm also going to put one more distance in here, and it's this distance to the axis of revolution. This distance is a fixed distance, and it is the fixed distance of 3. So no matter where I am, this purple line is always the distance 3. And what I want you to understand is that this little, let's look at little r first. I'm going to erase it there. Little r changes based on where you are along the curve. So I'm just going to move it up here. Remember, little r and big R extend from the axis of revolution to one of the curves. So this is little r. And you'll notice something. The little r line segment plus the pink line segment add up to 3. So this is the pink function. I'm going to put f for function. So take note, r, little r, plus the pink function will make 3, which means little r is 3 minus the pink function, or 3 minus that square root of y, because this is my pink function. So you guys, I just determined what little r is using line segments and piecing my graph together. Now I'm going to do the same thing, and I'm going to find big R. And generally, they follow the same pattern. So let's think about this. I've got this green line segment right here. The green line segment is the green function. Big R goes from the green curve. So I'm going to rewrite big R up here. This is big R. This gold line segment is big R. And check it out. Big R plus the green function, so I'm going to use a green f, also equals 3. Huh. Fancy that. There's like a little pattern here. Whatever you did for little r, the same thing is going to happen for big R. You're just going to use the outer function, right? So here, check it out. Big R equals 3 minus the green function, which is y squared over 6. So now I have my big R, 3 minus y squared over 6. I've got my little r. Little r is 3 minus the square root of y. That is the most challenging part of this entire endeavor, is determining big R and little r. Now I'm ready to plug it into my integral using my area function. So remember, a of x is going to be pi times big R squared minus pi times little r squared. So in my integral, it's going to look like this. I'm going to have pi, and then I'm going to have 3 minus y squared over 6 squared minus pi times little r, 3 minus the square root of y squared dy. And then the last thing I'm going to do is I'm going to figure out what are my limits of integration. And those are always based on the intersection points in a problem like this. So I'm going to go from the lower y to the bigger y. So the lower y is 0, the bigger y, according to Desmos, and I know that this is not precise, you would definitely want to make sure that you would pull the full decimal off of your calculator. Just for the sake of time here, and because it's on there, I'm going to just use what is given to me. But you would always, always, always want to graph it in your calculator, find the exact value, and go out to a minimum of 6 places while you're working. So don't do as I say, not as I do. But this is what you would plug into your calculator and evaluate to get your answer. I'm going to leave the setup here and not worry about plugging it into the calculator for the sake of time. But just a reminder, as you do plug things into the calculator, you would want to make sure that you type it in using the variable x as your y's. That's the language that your calculator speaks. It doesn't mean you are changing anything. You are just typing it in so that your calculator understands it. Now to finish out this video, we're going to take that same region and we're going to revolve it one more time, but this time we're going to revolve it around the line y equals -1. So again, I'm going to shade in the area that we're going to be revolving. It's this right here, but this time my axis of revolution is down here. Y equals -1. I'm going to label it using my little revolution symbol. Whoops. And now I'm going to determine my big R and my little r. And I'm going to remember that big R always extends from the axis of revolution to the outer curve. So my big R, and I suppose I should probably do this as well. I'm going to have kind of this, there we go, there's my mirror image. That'll help. My big R is going to go out to the green curve. So big R goes like this. Ooh, and this one is different, right? Because look, you have this -1. So what you're doing is you're taking the function, remember the function always goes from the x-axis to the curve in this case, which I'm getting ahead of myself. Let's review. This needs to be a dx setup. And the reason it is a dx setup is because I am perpendicular to the x-axis. So knowing that is a dx setup, let's go ahead and find our a of x. Now, remember, the function is always the distance from the x-axis or the y-axis to the curve. Here, from the x-axis to the curve, this is the function. And because it's a dx setup, my green curve is this equation. So I'm going to solve it for y. Y equals the square root of 6x. You guys, this is that square root of 6x function. But the r, the big R, has taken that square root of 6x and extended it and made it longer. So I'm going to add 1 to it because that's the distance down to that -1 line. Now this means that little r is going to have the same problem. It's going to be the function, so let's recall that little r goes to the inner function down to the axis of revolution. But this inner function now is going to be the x squared plus 1. You're going to add to it an extra distance. So sometimes we take the function and we add to it. We make it longer. And drawing a picture helps us determine what's happening. So x squared plus 1. It's 1 unit longer. So now I'm ready to set up my integral. I'm going to integrate, it's dx, so I'm going to go from 0 to the x coordinate, 1.817, which again, you would never want to use just that number. You would always want to go to the full 6 places or more. And I'm going to have pi times big R squared, wrap it up in parentheses, minus pi times little r squared. And this is what you would plug into your calculator to evaluate and find the volume. Now I'm going to trust that we're capable of using our Math 9 button at this point to find the volume. The setup is certainly the trickiest part. And once you have the setup, make sure you use lots of parentheses to get your final answer. And yeah, the more you do this, the more times you can practice, the more different kinds of problems you can have, the better you're going to get at determining what big R and little r are going to be. Lots of R's in that sentence. But no matter what, my encouragement to you is this. Practice will never make perfect, but practice will often help you get to a point where you're almost perfect, right? We can always learn more. The more you practice, the better you're going to get, the more confident you're going to feel, and the more success you're going to find as you go along. You'll never be perfect at your first try. It takes some practice. So keep at it. You can do this. You've got this.